Uh,
Hello, Raj.
yes, sorry, I was calling you.
No problem. I had to chair a session because the chairperson could not join for that
Yes,
session.
I'm aware. I'm aware.
Yeah.
I just wanted to let you know that there are people to join here also. So should I call them up?
Yes, that's a good idea.
Uh, so you could call.
I can also call them. Yeah.
Yeah, yeah. So let's divide it. There are two
Shank,
people,
Shankar
Shankar and
Narasimhan,
Arun.
yeah, and Arun Tangirala. So
Yeah.
I'll
So
call up Shankar Narasimhan. Yeah,
okay,
that
I'll
one.
call Arun then.
Okay. And Raj, how about the other tutorial that has also been started? The other parallel tutorial?
Shashi is there.
She is there? Okay, great.
Yeah, I think he will be managing.
Sure. Yes, I just now spoke to Professor Narasimhan. He says he's going to join soon. Professor
Yeah,
Tangirala is supposed to give the
yeah. I
two
spoke to
talks
him.
today.
He's saying he's joining in now.
Okay, great. It's great news. Should I go and check whether Shashi is doing it? Shashi.
No. Things are fine there. Things are absolutely fine. I'm in both the meetings.
Okay, great. Hello, Professor Tangirala. Good morning.
Yeah, good morning. Good morning. I'm joining actually from two places.
Okay. Yeah, this video looks a little weird because it just does the opposite of what it is supposed to do. It replaces your face with the view of Golden Gate Bridge.
Why is that?
I don't know. That's how it shows.
Okay. So what did the video show? Sorry.
At the place where your face should be, there was the view of the Golden Gate Bridge.
Oh, really? So
Yeah.
it is actually doing a wrong thing then.
Doing the opposite of what it is supposed to do. Yeah.
Oh boy. I think the background filter is not doing a good job. That's a problem.
Yeah.
So let me see if actually this is better. Let me actually see if it is it okay now?
Yeah, now it's okay. Now it's
okay. So I think the background filter went for a toss.
Yeah.
Okay, so I'll just start sharing the screen in maybe about a minute or so.
Sure.
Thanks.
Thank you.
So I think perhaps ready to start, or
Yes, I guess we are right on time. Already 11:30. Perhaps we can-
okay. So I think in the interest of time, we should get started. Even as perhaps participants join. So shall we get started, Dr. Devsatam?
Yes.
Or would you like to wait for a minute or so?
It's up to you completely, Professor Tangirala.
No, I think we can get started because it's already 11, close to 11:35.
Okay. So good morning all. I welcome you to this third session on this tutorial, series of tutorial talks. The title of this tutorial is Linear Model Identification Using Iterative PCA. And we are pleased to have Professor Arun Tangirala here as the speaker. This tutorial is jointly proposed by Professor Tangirala and Professor Shankar Narasimhan. They are from the Department of Chemical Engineering, IIT Madras. So over to you, Professor Tangirala. Professor Tangirala, you're not audible.
Yeah, thank you, Dr. Devasatam, for the quick and short introduction. As you mentioned, this is part 3 of our workshop. We had parts 1 and 2 yesterday, introducing linear regression in the OLS, WLS, and TLS frameworks. And then in the evening session, we had an introductory session to model identification, a tutorial on model identification using PCA. And this was the problem that we actually studied by and large. So we want to identify a steady state model between inputs and outputs, given their noisy measurements. So just to reiterate, as against a classical steady state identification, here the inputs are also known with errors. And the goal is to identify the model as well as estimate the noise variances in the input and output channels. And also I would like to emphasize, we assume the errors to be Gaussian wide, and this is typically called the output error model case. And what we learned yesterday is that the principal component analysis method is very suitable to solve this particular problem. It doesn't directly estimate the model, it instead estimates the constraint. Shankar, you wanted to say something?
Error variances are independent of the sample. So sigma squared yi and uj, no, I and j should be probably, I mean, gives the impression it is dependent on sample. It is not.
Right. So the general problem statement is that the error variances are actually different, right? It's only that PCA is good when all the error variances are identical. Yeah. So the problem statement.
No, I am talking about the subscript I and j.
Yeah. So
it indicates it's same for different samples. But what you want to actually emphasize is same for all samples. I mean, all output samples.
Oh, no. So the I here is the channel, no? I is not the time instant. K is the time instant. So as against the notation that you had for linear regression.
Okay, fine.
The I is the ith channel. So for example, I equals 1 means the first output channel.
Okay, yeah, perfect, yeah.
Okay, K is the one that is keeping track of the experiment or the observation. And this becomes useful for the dynamic case. So that's why this notation is adopted. Okay, so what we kind of learned yesterday, a quick recap of what we learned yesterday is that the standard PCA provides the total least squares estimates of the model parameters and noise variances. Of course, the optimization problem that I've given here was not stated yesterday, but this is the optimization problem that PCA is essentially solving. Yesterday, we obtained a linear algebra and another statistical perspective of PCA. But in the context of identification, this is the optimization problem that is being solved whenever you use PCA. And it gives optimal results for the equal error variances case, that is a homoscedastic case. And for the unequal error variances case, unfortunately, PCA fails to give optimal estimates. In fact, it also actually gives biased estimates. For very high SNRs, though, SNR is SNR stands for signal to noise ratio. For very high SNRs, the performance from PCA is satisfactory. So just to put things in context, in perspective here, I am showing the eigenvalues. I'm reporting the eigenvalues and the regressor matrices for two different cases of scenarios of SNR. One is for SNR 100, considered very high, and SNR 1 considered low. So as you can see here, what happens is the regressor matrix. So if I were to compare with the true regressor matrix, so this is the true regressor matrix that we are supposed to obtain. This is from yesterday's lecture. If you compare the regressor matrices for the two different SNRs, it's clear that for high SNRs, the regressor matrix is very close to the true value. But for low SNR, you can see a bias. Although I'm reporting here estimate from a single realization of data, ideally what one should do is do an averaging across maybe 200 or 300 realizations and report, and then you will be able to see the bias clearly. But I think even from the estimate obtained from a single realization, you can see a significant bias. It's not a coincidence that we obtain these estimates. Theoretically itself, PCA is not positioned to handle the unequal error variances case. Now, why does this happen, right? And different perspectives can be, reasons can be given depending on the perspective that you choose. From an optimization perspective, so if you go back to the optimization problem that you're solving, what is happening is that we are giving equal importance to the sum square errors there, right? So the true norm of the errors that we are minimizing, the error is Zk minus Z star K. Z stars are unknowns, they are the noise-free ones. Those, the errors that you are minimizing in a two norm sense are being given equal importance across variables. But in the unequal error variances case, we know that certain variables are obtained with more or measured with more precision than the other ones. That is the interpretation of unequal error variances. If you have equal error variances, then all variables are being measured with the same precision. Because of this different precisions in each sensor channels, we know already from weighted least squares literature, even from weighted total least squares literature, that the correct or the more appropriate way of handling or formulating the optimization problem is to not give equal importance, but rather use weights that are inversely proportional to the standard or variances of the respective channels. From a signal processing perspective, so it's interesting to actually subscribe to all these different perspectives and obtain different interpretations. So from a signal processing perspective, PCA is often seen as a filtering tool or as a tool that separates the signal space or the noise-free space and the noise spaces. Now, unfortunately, in unequal error variances case, PCA fails to achieve the optimal separation between the signal and noise space. And from a linear algebra perspective, what it means is that the basis for the null space is no longer obtained correctly. Of course, even in the homoscedastic case, the basis, homoscedastic case, the basis is not obtained correctly, but it is consistent, meaning as n goes to infinity, you will obtain the correct basis. Unfortunately, the consistency property would be lost when it comes to the heteroscedastic case. And you can also think of a geometric perspective that the data actually is stretched in different by different factors because of this unequal error variances and so on. Now, the interesting thing is, regardless of the perspective that you take, the remedy is the same. Okay, one remedy fixes all these problems, and that remedy is what we are going to discuss today, which is the iterative PCA. Again, you will find the same or the solution to be on similar lines as that in weighted total least squares. And just as a set of passing remarks, knowing the number of constraints a priori also does not aid an accurate estimate of theta. As you can see here, in this case, let us say I know that the last 3 eigenvalues here should have been 0, or I know that there are 3 constraints. Even knowing that has not helped us obtain an accurate estimate or an unbiased estimate of the regressor matrix. So that is also not helping. And in general, of course, you may not know the number of constraints also, then it becomes a challenge, because determining the rank of a matrix from its noisy version is also not possible. That is, determining the rank accurately. Why is that? Because no particular pattern, such as 0 eigenvalues or equal eigenvalues or equal singular values. Yesterday we did observe, and I did mention that for the homoscedastic case, one does not obtain 0 singular or eigenvalues, but rather obtains equal singular values. That pattern is also lost in the heteroscedastic or the unequal error variances case. And the point is, we are working with Z, whereas we should be working with Z star. And the main point is that this error here is of full rank, it is orthogonal to X, and it is also has unequal variances. That's the main challenge. So what has been a practicing solution to guess this rank of X? If you skim through the vast PCA literature, you will find a number of heuristics. And some of the popular heuristics are the unity eigenvalue, or the scree plot, or the scree test, or the percentage variance explained, and so on. I mean, you can come up with your own criterion for choosing or discarding the principal components or the eigenvalues. We do not want to work with such heuristics. We want to ask if it is possible to theoretically figure out the rank of or the number of linear relationships in the matrix by seeing through the noise. So is it possible? Does a theoretical solution exist? And the answer to that is yes, and that is what is iterative PCA. Now, it's about probably more than 13 years old since iterative PCA has been proposed. And the basic idea, if you look at an IPCA, is to scale the data by the square root of sigma e, inverse of the square root of sigma e. What is the sigma e? It is the noise covariance matrix of all the inputs and output channels, and then implement PC on the scale matrix. This is exactly the idea that you would find in weighted least squares or weighted total least squares and so on. And why should this idea work? Well, the answer is simple. It converts a heteroscedastic case to homoscedastic case. It's as simple as that. But where do we obtain the sigma e from? That's the issue, right? This is $1 million question. It's not easy to obtain sigma e in most applications, and maybe a few applications you will be able to obtain sigma e by performing some experiments on the sensors. But by and large, we do not have such privileges. So the alternative is to obtain sigma e iteratively. What do we mean by iteratively? I'll explain shortly. But this is also well known in the weighted least squares literature. Now, I keep saying it is well known. Was actually IPCA inspired by weighted total least squares? I'm sure Shankar will be able to give you a lot more historical facts about it. But as far as I know, because I've seen this iterative PCA developed by Shankar since his sabbatical at Alberta. It was about maybe 13, 14 years ago. And I do not remember any discussions on the weighted total least squares at that time. But I think over a period of time, parallels were discovered. Am I right, Shankar?
To some extent, yes. But the idea of scaling and remapping it to a simpler problem was always what I call the strategy we use in solving problems. So in that sense, yes. Yeah.
Fine. So are there terms and conditions under which this method works? Of course, there are certain identifiability conditions. And what about optimality, right? Because we do not know sigma e. If we know sigma e, then there is nothing to worry about optimality. All you do is you scale the data and then you run your PCA, and anyway, PCA is solving the optimization problem. It is conditionally optimal. I don't know if, Shankar, you managed to prove the complete convergence. I thought, you could prove optimality for each component of the iteration.
Under conditions, yeah, under additional stipulations, yes. We can prove optimality, convergence of the algorithm to the optimal solution. Optimality, we don't know it's globally optimal or not.
Okay.
But it does converge.
Okay, so let me explain first the terms and conditions, assumptions and framework, and then this iteration, and then you will understand what Shankar means by convergence. So the framework, again, to put everything together, we are interested in in identifying a system that is governed by equation 7. Z is your combined input and output vector, and they are tied together by this constraint, and we obviously want to estimate the constraint matrix A, and the dimension of A and the dimension of these noise-free variables, as I mentioned early on in my talk yesterday, depends on whether the process is at steady state or is experiencing dynamics or transients. Under steady state conditions, the number of columns of A, which is M, is equal to the number of outputs and inputs. So M is NY plus NU. Whereas under dynamic conditions, the number of columns in A or the dimension of Z star depends on the order of the system. And that is what we are going to talk about in the evening session today. So we will focus on the steady state case in this lecture. And as I said earlier, we are confining ourselves to the output error case, where we assume all the measurements are corrupted with white noise sequences. Of course, they're spatially uncorrelated. So you do assume sigma E to be full rank. And in particular, we will restrict ourselves to diagonal sigma E's, because that's an easier problem to solve. I think the non-diagonal sigma E's are a bit more challenging, and you have to ask what is the source of the non-diagonal sigma E to solve. We have solved the non-diagonal sigma E's under certain conditions, but that would be outside the scope of this talk. So I'll restrict myself to the diagonal sigma E. And for the deterministic, or there should be ZI star, not the noise-free signals or the deterministic signals are assumed to be quasi-stationary. Quasi-stationary essentially means that the signals are having bounded amplitudes, and that their autocorrelation actually becomes independent of the lag over at large times, and so on. So basically some kind of a well-behaved signals with properly defined temporal covariances and means and finite variances. Now, the key condition that comes into play for IPCA is identifiability. Now, why does this identifiability come into play? And then I will talk about the condition itself. Look at it this way. We are interested in estimating both the constraint matrix A and sigma E, as against only estimating A like we did yesterday. So obviously we are now keen on extracting more information from the data as against just estimating A, which means that we need a sufficient amount of redundancy, and that is what essentially the identifiability criterion is saying. If you start with estimating A, suppose there is no redundancy in the data, then the question of estimating A itself is gone. So estimating A itself calls for some redundancy in the data. Over and above, there is this additional constraint on the redundancy. Where does the redundancy come into play in this equation 9, which states identifiability condition D? So D is the number of constraints we have. More the constraint, more the redundancy in the data, right? So you have, if you have more constraints, that means you have more variables than needed. So this constraint here is reflective of the additional redundancy that is required to estimate sigma E. If you know sigma E, this identifiability condition is not needed at all. So how does this condition come into play? What is the relationship between D, the number of constraints, and the number of variables M, is the mystery at this moment. We will unravel that mystery very soon when we talk of estimating sigma E given A. So that is from where this condition actually pops up. And you can say that the LHS of this constraint here is the number of diagonal plus the off-diagonal elements of sigma E corresponding to the dependent variables only. Okay, because D is also telling you how many dependent variables are. That is one interpretation. Anyway, so we will talk about this condition when we discuss estimating sigma E from A. So let's get into the basic ideas governing iterative PCA. As we know, and as we wrote yesterday, in terms of the stacked grand matrix Z star, which consists of all variables and all observations, the constraint that we wrote, A Z star equals 0, can be written as Z star A transpose equals 0. And as I mentioned earlier, for the steady state case, Z star is assumed to be n by m. N is the number of observations, m is the total number of variables, and A is B by m. Now, what we have is measurements of Z star, which is Z. So this is what we have. Under open loop conditions, what we mean by open loop conditions is that Z star and E are not correlated with each other. So that's an important requirement or condition to keep in mind. You can add that also to the list of conditions that I stated earlier. Because if the process is under closed loop, then the inputs and outputs are going to be correlated, and there is every chance that the noise variances, that the errors in E, the E matrix, and Z star, the noise-free measurements in Z star are correlated. So that's going to be a problem, right? Because U is going to be driven by Y. So let us keep that out of the picture. Under open loop conditions, you essentially have this relation between sigma Z, which is the noise covariance of the measurements, and sigma Z star, which is the covariance of the noise-free measurements. Because of quasi-stationarity assumption, sigma Z star exists and is also finite. And sigma E, of course, exists. So this is the relation that you obtain. And this is also going to tell us why the noise plays a spoil sport in identifying the number of constraints. Why? Because the eigenvalue of sigma Z is now going to be some complicated mixture of the eigenvalues of sigma Z star and sigma ZE. Only when sigma E is diagonal, then the eigenvalues add up. Even in that case, the situation is complicated. In fact, if sigma E is not diagonal, then this result also is going to be a problem. So the eigenvalues do not necessarily add up, that there is an issue there. So you will have to actually diagonalize the sigma E and then use this result. So you understand one of the main reasons why we work with diagonal sigma E's. So what is happening here is, imagine that this noise term was missing or absent. Then you would search for 0 eigenvalues. Now you will have to search for eigenvalues shifted by the eigenvalues of the sigma E, but you do not know sigma E. If you know sigma E, then in fact you can either scale, right, the matrix with sigma E, or you can say that I will search for eigenvalues shifted by exactly the eigenvalues of sigma E. So I know that the 0 eigenvalues will be exactly shifted by lambda of sigma E. But still scaling would be required in order for us to get the constraint matrix right. Am I right, Shankar? I think that part probably applies. Because eigenvector calculations may take a beating if you don't scale.
No, this has to be, sigma E has to be not just diagonal with equal elements on the diagonal, which means the scale of the identity matrix.
No, my question is
13. The 13 result is valid when sigma E is a scale of the identity matrix only. It cannot be just a diagonal. It
Just
has
a
to be a
diagonal.
scale of the identity.
No, but
You can't prove otherwise. This eigenvalue result is valid when sigma e is not just diagonal, but diagonal with equal entries on the diagonal.
okay. So then there is so this 13 has to be, I think, corrected. But so okay. So I think this equation 13 has to come after we scale. It's better to do it that way. Correct. Yeah. So I'll change that in the slides. Correct. It's correct. Okay. So please note that this should be actually identity. If sigma e is identity or a scaled version of identity, then equation 13 applies. So with the assumption of diagonal, but I would replace diagonal with a scaled identity. So only under this specific condition that does the eigenvalue add up. But we know in the heteroscedastic case, this does not apply to sigma e. And you also now understand why in the homoscedastic case, all the eigenvalues are actually shifted by the equal amount, which is equal to sigma square e. So what is that now we have to do to achieve this? So our goal is to start from here, or rather equation 12. We know that sigma z is sigma z star plus sigma e, and we want to reach sigma, somehow we want to make sigma e either equal to sigma square e times identity or identity itself. So the key idea in moving from equation 12 to 13 is to scale the data with some suitable scaling matrix. Now, scaling essentially is different from filtering. Filtering is a temporal operation. Scaling is essentially adjusting the amplitudes at each instant. But for each channel, you will apply a different scaling factor. How do we want to choose a scaling matrix? The eigenvalues of the scale measurement and the scale deterministic covariance matrix should only differ by a known constant. That is how it should be. And additionally, the scaling matrix should not reduce the rank of sigma z star. So these are the two important requirements in choosing this scaling matrix. Now, a nice solution, I'm not so sure if this is the only solution, but a nice solution is obtained, and that is what leads to IPCA. And it's also in line with the weighted total least squares, which is that S equals sigma e to the minus half. That is, if you set the scaling matrix to the inverse of the noise covariance matrix, then we can achieve what we want. Why is that so? Because if I write here sigma e minus half z equals sigma e minus half times sigma z star plus, so it's not z star, this is z star, plus sigma e to the minus half e, then when we write, so if you call this as some z scale, then sigma z scaled would be sigma z star scale plus identity. So this is the accomplishment that we have by choosing the scaling matrix as sigma e to the minus half. Now we can straight away say that the lambda of this is the lambda of the noise-free measurements plus lambda of identity. Of course, lambda of identity are all unity eigenvalues. So what this means is that if I scale the data with sigma e to the minus half, the zero eigenvalues corresponding to the D0 eigenvalues will now shift to D unity eigenvalues, and that's the main result in IPCA. And now you know exactly what to search for. Okay, you can think of this as a homoscedastic case where all the sigma square e's are set to 1, but you know now what to search for. You just search for unity eigenvalues in place of zero eigenvalues, and that is the main point to remember in IPCA. But of course, the question that begs attention is, where do we obtain the estimate of sigma E from? That's the main question. And a solution to that is to estimate sigma E and A iterative. If you have, of course, other solutions, do let us know. But this is a standard approach that is also used in weighted least squares and weighted total least squares. Then we move on to the question, how do we estimate sigma E given A? Right? A is a constraint matrix. Sigma E is the noise covariance matrix. A lives in a lower dimensional space. I mean, A is of lower dimension. Okay, I'll talk about that now in this slide and the next slide. The first step is to furnish an initial guess of the A, that is the size of A. Of course, the column size is known. The number of rows D, you furnish an initial guess. In other words, you guess rank of Z star. Then, given A, you can estimate sigma E using a maximum likelihood approach. Let me go to that and then come back to the third step. So how do you estimate sigma E given A? Let us say that your guessed order is correct. Okay. At some iteration, hopefully you have guessed it correctly, which means that it straight away tells you that in IPCA, although the tagline is search for unity eigenvalues, you will still have to guess the number of unity eigenvalues and then verify indeed if your guess is correct. So let's say you got your correct guess, and at some point in time in your trial, in your search, then go back to the equation governing Z and multiply both sides with A hat I. I is now, sorry, the iteration here. Please don't mix up this I with the I that I used early on in the problem statement. What happens is then, because you have, let us say, arrived at some point, A hat of I is the as the correct solution, then A hat times Z is nothing but A hat EK. And this is what we denote by, we call as the residuals obtained from the constraint. Of course, if you know the true constraint, that is, let us say the true constraint is A naught Z star is 0. We are just assuming that at some point you have hit upon A naught, which is, of course, in reality not correct. Okay. So this would be in reality only an approximation. Please keep that in mind. From the residuals that you obtain, right? When you apply A naught to Z star, you will get 0. When you apply A naught to Z, you will get A naught EK. We assume that A hat I and A naught are identical at some part of your iteration. Then what you get are the residuals RK. And now we exploit these residuals to estimate sigma I. Again, this is pretty much like what you see in ordinary least squares. In ordinary least squares also, when we want to estimate the variance of the errors, the equation errors there, regression errors there, you will have to turn to residuals and you use the estimate of the variance of the residuals as, and you can show that it is an unbiased estimate of the sigma of the EK there. Pretty much in the same way, you can use your constraint residuals to estimate sigma E. And how do you do that? Using equation 7. Okay. So equation 17 allows us to relate sigma R to sigma E. But then we have to remember that RK is of lower dimension as compared to EK. See, EK is M by 1, whereas R is D by 1, which means that sigma R or RK lives in a lower dimensional space. So you have to go from lower dimensional space to higher dimensional space. It cannot be done without imposing additional constraints. And that is where the identifiability constraint comes into play. So subject to that identifiability constraint, this problem becomes identifiable. What problem? Estimating, recovering sigma E from sigma R. And how do you recover that? You set up an MLE. Essentially, you say, I want to maximize the likelihood of the residuals, and you, if since E case are assumed to be Gaussian, R case are also Gaussian, and then you set up the standard MLE for the Gaussian case, and the log likelihood function is given in 18 here. So if you talk of the condition that is required to solve, so how many unknowns do you have in sigma E? In sigma E, so remember, sigma E is symmetric matrix. Since it is M by M, you have actually, strictly speaking, M times M plus 1 by 2 elements to be estimated. Whereas in sigma R, you have only D into D plus 1 by 2 unique elements. Because that sigma R is also symmetric. If you assume sigma E to be diagonal, then it becomes easier. If it is non-diagonal also, you should be able to solve it, but then you will have to know where the entries are. And again, doesn't matter how many non-diagonal entries you have, at most you have only D into D plus 1 by 2 equations. So for the simplest case, when sigma E is diagonal, you have M unknowns. So you'll have to recover this M unknowns, and you need M equations. So that is where the identifiability condition comes about. So you know the mystery of D into D plus 1 by 2 and the connection with M. Shankar, do you want to add anything to that?
Yeah, no, Arun. That's it. We have pretty much covered it.
Okay. So let's get back now. Subject to the identifiability condition being satisfied, you can now recover sigma E from sigma R. Using an MLE method, there is also a least squares method that you can set up, because after all, this is only an approximation. So you set up D into D plus 1 by 2 equations and solve or estimate for the M unknowns in a least squares sense. Typically, your D into D plus 1 by 2, you want it to be over determined. So D into D plus 1 by 2 will be greater than M. A least square solution is computationally much better as compared to MLE. Once you obtain your sigma E, go back and scale the data, and then iterate. That's it. That is the basic idea. You start. How do you kickstart your algorithm? You start with ordinary PCA, which generates an estimate of A. Once you have an estimate of A, you can get an estimate of sigma E using the procedure that I just went over, and then you iterate. Okay, so this is the procedure for the IPCA algorithm. You stack the N observations as usual, as you do in PCA. Set your iteration counter to 0. Initialize with the estimate of constraint matrix from standard PC of raw data. You don't have to standardize. Generally, as I mentioned yesterday, in PCA, it is a common practice to standardize, meaning mean center and unit variance or unit 2 norm of the measurements. You don't have to do that. You can just use the PCA on the raw data and then obtain the preliminary estimate of the noise covariance matrix. Subsequently, you scale the data using the inverse of square root of noise covariance matrix. That is, now you set Z to sigma E hat minus half Z. So you update, and now you perform PCA. So this is your ZS scale data, and you perform PCA on ZS, the scale data matrix, and then extract the constraint matrix and continue, repeat 2 to 4 until convergence, acceptable. Some tolerance criteria have to be met. And in all of this, you will have to specify the number of unity eigenvalues. Okay. And if the number of unity eigenvalues matches, that is, your guess matches the unity eigenvalues that you get, then you don't stop. So there is an important thing. You don't. If the moment you're satisfied, you should not stop there. You continue to increase it. So if you're starting with the lowest possible D, lowest possible guess. What is the lowest possible guess? The lowest possible guess is dictated by the identifiability criteria, right? So if you have 5 variables, the minimum number of constraints that you need to have to satisfy the identifiability criteria. So if m equals 5, then D minimum, your minimum guess should be 3. Because if D guess is 2, then 2 into 2 plus 1 by 2 greater than 5 is not satisfied, right? So you know the number of variables, therefore you start from the lowest guess and increase it. I'll talk about the choice of the initial guess very soon. You increase it, and then there is a pattern that will emerge, and then you will be able to correctly arrive at the correct guess on the number of constraints. So there is an iteration involved on D guess, but there is a systematism to it. It's not ad hoc like in your heuristic methods like scree plot and so on. Okay, I'll talk about that very soon. But let me now go to the main results. And before I show you the results on the case study, let me tell you that you do have the option of standardizing the data in the standard way. But that is redundant because IPCA is anyway standardizing your data with the square root of the standard deviation of the errors, right? And even if you know the number of constraints, it is beneficial to implement IPCA. Let me say that. And scaling the data, of course, with the standard deviation of errors is the key, and it amounts to a suitable rotation of the data matrix. So you can think of this as from a geometrical standpoint. Once you estimate your A, you can kind of assess the accuracy of the estimate of A, at least in the simulation case, where you know the true constraint matrix. There are two ways of looking at it. One is a subspace where you measure the angle between the subspaces spanned by A naught and A hat. Or you can measure the distance between A naught and A hat. So this is a distance measure. Again, the definition is given here. This was proposed in the original IPCA paper. And the regression matrix, as usual, can be recovered once you have the convergence on D guess and your A hat and sigma E. You partition A hat as we did yesterday, and then recover your regressor matrix. So let's go back to the flow mixing example that we have been using since yesterday. And now the problem itself satisfies the identifiability requirement. So you have 5 variables and 3 constraints. So which means that, yes, you will be able to estimate sigma E and A. What I mean by this is you will have to ask if the original problem that you're taking up indeed meets the requirements of estimating sigma E and A. It's not that always you will be able to implement IPCA. You can implement PCA all the time as long as there is even one constraint. Suppose with these 5 variables, I had only one constraint. Then unfortunately, you cannot implement IPCA. Am I right, Shankar? Even with 2 constraints, you cannot implement.
Correct.
Yeah.
Because you can't estimate sigma.
Exactly. So when you choose a problem to implement or to demonstrate IPCA, please keep this in mind. You will have to make sure that the identifiability criteria is satisfied. Okay, so this is some tidbits about some information about data generation, how we did this, and we make sure that the noise is added in such a way that the signal to noise ratio is 10. And it turns out that these are the numbers to guarantee signal to noise ratio 10 for each measurement. That means in all the channels, input output channels. So here we don't have inputs and outputs notion, just dependent and independent variables. And here are the results from the implementation of IPCA. So I'm reporting the singular values here. Whether you get unity eigenvalues or unity singular values, it's one and the same. So at the top here, I'm reporting the singular values. I guessed D equals 3, and I got 3 unity eigenvalues. Ideally, I should not stop at this. I should guess 4 and see if I get 4 unity eigenvalues. If I get 4, then I'll have to actually go further. Of course, it's not possible to have 5 constraints. You need to have at least one independent variable. So in this case, I should guess the next one, d equals 4. I didn't do that because I know the setup, and I'm just showing, the purpose is to show you what happens when you implement IPCA as against PCA with a standard scaling. So you do get 3 unity eigenvalues. Whereas with PCA with standard scaling, you get nearly equal eigenvalues. At least the last 3 are nearly equal. You can do a hypothesis testing to figure out if these 3 can be actually considered equal. So there are results which tell you how to conduct that hypothesis test. You can refer to the book by Jolliffe. We also implement that in another paper of ours, which I'll talk about in the evening. But here, although the situation is that we have a heteroscedastic case or the unequal error variances, you still get nearly equal eigenvalues from PCA because the SNR is high. I'll show you shortly what happens in a slightly variant of this example. When you lower the SNR, what happens? Okay, so you can see with IPCA, we are successful in detecting the number of constraints, and the covariance matrix is recovered pretty close to what we used, 0.1, 0.1, 1.3, and 0.2 and 0.5 are the true values. And the regression matrix, I suppose by now, if you have been following the lectures, I think it would be known by heart. 2 and 3, 1 and 1 and 1 and minus 2. So good to know. Now let's talk about the impact of d-guess. Remember, d denotes the extent of redundancy. That is what is an important perspective to subscribe to. And of course, it should satisfy the identifiability criteria. So what does a large value of d mean? It implies that you're estimating more parameters. Obviously, there are more number of elements in the constraint matrix, and that means you are going for a higher model complexity. Remember that. Lower the d, yes, merrier the situation because you have fewer parameters, but you may actually not be satisfying the identifiability criteria. Suppose you choose a value of d and it satisfies the identifiability criterion, and the number of unity, then the number of unity eigenvalues will be equal to d guess. So let's say d naught is a true number of constraints for a problem, and you choose d guess to be less than d naught, then you are guaranteed to get as many unity eigenvalues as you guessed. But it is an underfit. So obviously, in order to make sure, like in standard system identification, you will have to check, you'll have to increase the model order and check whether a higher model order is actually giving you the a better fit while still satisfying certain criteria. And that is what residual analysis will actually tell you. Shankar will talk about it tomorrow. How do we combine the standard procedures in identification and use that for resolving d-guess? But even if you don't do a residual analysis, the method is you increase d-guess until you exceed the true value. How do I know that how do we know that we exceeded the true value? The moment you go beyond the true value, the unity eigenvalue condition breaks down. That is when you have overfit, which is a nice thing. So there is a inbuilt underfitting and overfitting mechanism that you see here. And a more rigorous approach in all of these trials that you do with d-guess is to conduct a hypothesis test on the equality of d eigenvalues instead of just visually observing it. Okay. So I'm omitting the details of the hypothesis test here. You can refer to the the book by Jolliffe or our own paper that we published in 2020. We use the results available in the literature to implement the hypothesis test. Okay, so hopefully it is clear. All you do is you start, you can go from low to high or high to low. if you start from low, you will have to watch out for the guess beyond which the unity eigenvalue condition is broken down. If you start with a high value of D, in which case your identifiability criterion is already satisfied, then you keep decreasing until the first time the unity eigenvalue condition is met. So either way is okay. Okay, so let me conclude with a second example where I show you the effect of different scaling strategies that we use. And this example is a slight variant of the earlier blending example that we saw. And you will also see this example in the original or the seminal IPCA paper. We use base value of 10 for the independent flows 1 and 2, with standard deviation of 1 and 2 for the base value of 10 is used, and then standard deviations of 1 and 2 for the respective flows. And then for the remaining, the remaining flows are generated according to the equation given in 25, and the noise variance is adjusted such that the SNR is 10. The true noise variance that was used in simulation is reported here. And in this table, we are comparing the results from PCA with different scaling strategies and IPCA. So if I apply PCA to the data without any scaling, what are the metrics telling me? Alpha and theta. Alpha and theta are the metrics telling me how close my estimated constraint matrix is to the true one. Alpha is a distance measure, theta is an angle measure. We don't, obviously both of them have to be very close to 0, but instead of worrying about how close they are, let us compare. So you can see that with respect to alpha, the distance measure, PCA, in fact, with no scaling, this is a bit surprising. The distance wise and angle wise, it is better than without scaling. So without scaling, I have a better result. I don't know, maybe Shankar can explain this. But the PCA with the known sigma E naught scaling. So this is the gold standard, okay? So here is our reference. If I knew the true sigma E, then I would scale the data with sigma E to the -half and implement PCA. And you get 1.62 as a distance measure and 0.028 as the angle measure. So pretty close, better than PCA with any of the other scaling strategies. And you can see that the eigenvalues are very close to unity, the last 3 eigenvalues. Now compare this with IPCA, right? In IPCA, I do not know sigma E, but I'm able to actually get a performance that is very close to the reference PCA. Of course, that you get a better or a lower distance measure, I think, is only coincidental. I think one has to compare across many realizations, and then there will be definitely the PCA with the known sigma E will give you a better estimate. But instead of looking at the numbers at such micro level, let us look at the order. They're very close, and interestingly, again, you get unity eigenvalues. So which means that the performance of IPCA is as good as PCA with known sigma. And that's very, very encouraging, right? And the estimated sigma E is given here. So you can compare with the known, so the sigma E that we used in simulation. Now, this is for SNR 10. When I lower the SNR, what happens? Let us see. Obviously, the performance deteriorates quite badly here. So you can see in both these cases, the performance is very bad. You can see the high values of alpha and theta, whereas IPCA is pretty close. Of course, now the distance between IPCA and the benchmark or the reference, in the performances has increased because of lower SNR, but it is not very drastic. It's pretty close. And likewise in theta as well. And even under such low SNR conditions, you obtain 3 unity eigenvalues. That is, you are able to estimate the number of constraints correctly. And that's the beauty of IPCA. Very robust, able to handle even low SNRs, as low as unity. So hopefully, this has given you a good overview of the idea of IPCA and what are its features, what are the things to watch out for. And we have MATLAB scripts available for you to implement IPCA and play around. We also have a GUI, as Shankar mentioned yesterday in the opening talk. The GUI is a work in progress, but yes, we have reached a stage where we can distribute and you can play around with it. Do let us know if you're interested. But that's about it for today's lecture. And the floor is open to questions. I'll just leave you with the summary slide. Okay, so any questions? Did you want to add anything, Shankar?
Not really, Arun. I think although the example chosen was small, that is only for illustrative. You can actually, it scales also for number of variables. Even if you have 50 variables, for example, I mean, the method seems to work quite effectively. We have done it for 150 variables, 200 variables problem that we have actually done, sigma estimation. So that is what for spectral data, when we are estimating sigma for each wavelength in absorption data and so on. So it seems to actually work quite well, even for large dimensional problems.
Okay. Yeah, I think I have seen that example in some other presentation of yours. But how critical would be some of the assumptions? For example, the Gaussian distributed errors and so on. For example, in the spectroscopic case.
I see. Independently, it's very difficult to verify whether the error variance is Gaussian. But we just go ahead and apply. It seems to reproduce the sigma quite well also.
So is it possible to do a post checking of the assumption of Gaussianity from the residuals?
I don't know whether we can do a normal probability plot of the. I mean, it's very difficult. I don't know whether we have samples, right? Multiple samples. Okay. You see, the signal, we are not making any assumption regarding the signal. Signal can be arbitrary. So you can't plot the data and see it. You have just one estimate of sigma.
No, I'm not saying plot the data. I'm saying plot the residuals. Because the residuals will be free of the effects of.
Yes. Residuals, you can do a plot. Just like you do in ordinary least squares. See whether the normal probability plot is obeyed or not.
Right. Okay, so I don't see any major questions. And also the number of participants is lower than what we had yesterday.
Yeah, just to remind the audience that unlike the regular sessions, here you can just unmute yourself and ask questions.
Yeah, we would be really happy to hear their voices. With all the online classes, the text-based questioning is becoming boring.
Yeah, true.
So I don't hear or see any questions from the participants.
Yeah, maybe I can ask a quick question just out
Sure.
of curiosity.
Please.
This iterative PCA, if I'm not mistaken, PCA also needs eigenvalue, eigenvector computation, right? Because essentially
Correct.
it's singular value decomposition.
Yes.
So all these eigenvalue, especially eigenvector computations happen with power method, which is iterative in itself. So it will have, it's impossible to avoid errors in computing these eigenvectors. So when iterative PCA is calculated, do these errors is there a possibility of the errors getting accumulated and somehow going out of bounds?
Theoretically, your question is valid. But I believe that the computation of eigenvalues and eigenvectors are fairly robust. I don't know, for large dimensional problems, maybe it's possible. Shankar, did you want to comment on that?
Yeah, that's if we have to use what's called incremental SVD for handling what we call large data sets, then the error accumulation has to be controlled carefully. But if we are working with small data sets, the existing algorithms for eigenvalue computation are extremely accurate. I mean, they take care of this problem. Power method is not necessarily the only method that is used. I mean, I don't know if you're computing a few eigenvectors and a few eigenvalues out of the overall, then the power method is okay. Otherwise, you don't do that. Normally, for a complete set that we require for this problem, the complete set of eigenvalues and eigenvectors, then only we will be able to find out the smallest eigenvalues.
It's not the so-called economical option in MATLAB.
Yeah, right. So power method may not be used for this if you look at the full computation. But these are usually taken care of in the eigenvalue computation routine itself. I mean, numerical fellows mathematicians have done a very, very good job.
Yeah, Francis method and some Krylov subspace method also are used for this eigenvalue.
Fair amount of balancing of the matrix, do householder transformations, and then finally arrive at it. I mean, they really do a whole lot of things to control the error propagation.
Well, primarily, I think because it's so fundamental to all applications everywhere, that there was a need, and there has been a need to make sure that the eigenvalue computations are as accurate as possible. So that's why I think so much effort has gone into accurate computation of eigenvalues and eigenvectors. But yeah, I think for large dimensional matrices, I don't know what the literature says. I've not read that. Then, as maybe Shankar says, you'll have to look at incremental SVD and so on.
Right.
There's just one thing, maybe Arun, that I want to point out, that when you wrote the equation 13 or something, when you compared the sigma E of the data to the sigma E of the scale data plus identity matrix, right?
Right.
What we call the eigenvalue shift theorem.
Correct.
One thing that usually, even in the paper, we have not, I mean, of course, it's stressed, but probably needs to point out again. It is just not the eigenvalue. If you look at the eigenvectors of sigma z, scaled value sigma z, they will be the same as the eigenvectors of sigma z star. So literally the null space of sigma z star is actually captured by the eigenvectors of sigma z, corresponding to the smallest eigenvector.
Correct. That's correct. That's also important if you want to obtain a constraint matrix correctly.
Yes, correct.
Yeah, probably I'll add that to the slide, because that's equally important. And I think that also kind of explains why, even if you know the number of constraints, you will not be able to get the regressor matrix or the constraint matrix accurately unless you scale.
Yes, correct. Yeah.
Okay, so I think we can conclude the session.
Yeah. So I'll just take this opportunity to thank you again, Professor Tangirala and Professor Narasimhan. We look forward to the future lectures in this tutorial series. The next event in ICC is the plenary talk at 2 o'clock, which is called Intelligent Autonomy and Cognitive Robotics by Dr. Balamuralidhar Purushothaman. So see you all at 2 o'clock. Till then, bye and take care.
Yeah, thank you. Thank you, Dr. Devasattam.
Thank you. Thank you
Thank you
so
very
much.
much.
Yeah.
Thank you.
So I'll end this session.
Yes, yes, please.